person who has ever lived. What did he exactly do? Well, Albert Einstein made the theory of relativity, which is often regarded as one of the most influential theories of all time. It completely changed how we view the world and how we think it works. But what is the theory of special relativity? Well, this video is going to introduce you to the principle of relativity that lies at the heart of Einstein's theory of relativity, a seemingly simple idea that has absurd consequences, such as time travel. This video is just going to introduce you the principle of relativity and how it leads to the invariance of the speed of light. Stay tuned for my next video for how does it imply time dilation. Now let me ask you a question. What if you and your friend are playing tennis here on land? Alright. Now imagine a same situation if you're playing it on a boat. Would this tennis game be any different than this tennis game? By the way, this boat's moving at 30 miles an hour. Would this tennis game be different than this tennis game? Would there be any difference between these two tennis games? Alright, let me ask you another question. What if you're on land and you throw a ball up and you're doing the same thing on a jet going 600 miles an hour? Would there be any difference? Would the ball land exactly in your hand? Alright, let me ask you one more question. What if you're here on Earth, you go into a microwave to microwave some food. I do the same thing here on another planet that's moving at 5% of the speed of light away from Earth. Would the microwave act differently because you're on another planet? Would there be any difference? Well, the obvious answer is no. Even though you're moving, the laws of physics seems to hold. And if you accept this idea, the idea that even if you're moving, every single reference frame can all the laws of physics follow in every single reference frame. And if you accept this idea, you pretty much accept the idea that's at the heart of relativity. And what is this idea exactly? Well, to put it in words, it is all the laws, every single law. There is no exception to this. All of the laws of physics are the same in uniformly moving reference frames. So basically, it's just what we said before, that no matter how fast you're moving, where you're moving, how you're moving, as long as you're moving in uniform motion, meaning a single constant speed, no acceleration or stopping or anything, as long as you're moving in uniform motion, every single law of physics will work for you. Everything will work the same. Now this seems intuitively obvious. You already know this. How does this lead to relativity? Well, I want you to know that we're going to have to go back in time to the 19th century. So the 19th century was a person named Maxwell. And he made the Maxwell's laws of electromagnetism, which combined electric forces and magnetic forces into electromagnetic forces. It also predicted the existence of electromagnetic waves, which travel at a speed c, which was well known at the time as the speed of light. There are many different kinds of magnetic waves, from light to X-rays and gamma rays and UV light. But they all travel at the same speed, c. The only difference is their wavelength, which is the distance from one throw to the other throw. So physicists in the 19th century trying to solve the problem, speed c relative to what? Now imagine you're standing here and there was a train, or your friend was on the train, and he threw a ball that's going 5 miles an hour, and the train is going 30 miles an hour. to you, the ball is going 35 miles an hour because of the motion of the train. But to your friend, the ball is only going 5 miles an hour. So which one's right? Well, according to Newton, they both are right. The motion of the ball depends on one's frame of reference, which means there's no such thing as universal motion. Everyone could have different values for the same motion, and they both could be right. Like 35 and 5, they're both right. Just said depending on your frame of reference. Well, Maxwell said that electromagnetic waves propagate at speed c. Well, speed c relative to what? If your friend was shining a light instead of throwing a ball, wouldn't you get a different speed because of the motion of the train? So speed c relative to what? Me or my friend? Well, scientists proposed the idea of the ether, a very mysterious medium which light goes through. Like how sound propagates through air, light will propagate through the ether. It would be speed c relative to the ether. Now, there have been numerous experiments in the 19th century in order to prove the existence of the ether, but all of them failed. One of the most notable experiments was the Michelson-Morley experiment, which proved once and for all that ether wasn't a real thing. So speed c relative to what? Now, Einstein. Principle of relativity, which is the one that all laws of physics are the same in all uniformly moving reference frames, it says that all the laws of physics, one of the laws happens to be Maxwell's law, and the Maxwell's law implies of electromagnetic waves that's traveling at speed c, which means no matter what reference frame we're in, you will see light traveling at speed c. Light will always be at speed c. Now, how could this be? Imagine this was light. It's coming towards you. This is you. This is your friend. This is your other friend. You are at rest relative to the earth and the light. Your friend is moving 600 miles an hour relative to the light. And your other friend in the rocket ship is moving at half the speed of light relative to the light. And you all set up an experiment in order to measure the speed of this light. As you know, speed is equal to distance over time. So the speed has to be the same. That's what Einstein's relativity principle implies. Which means the speed has to be the same. But how can this be? This he's moving at 0.5 c, which means by the time the light takes to reach him, he will already be like over here, while this guy will stay here. So the distance for this guy will be less than the distance for this guy, and the distance for this guy would be in the middle. They all have a different distance for how far this light travels. So how can the speed be the same if the distance is different? Well, if you look at the second term in the formula, time. If the speed could be the same if the distance is different and the time is different, which means this guy's moving so fast that his time is different. Newton already said that the distance depends on one's frame of reference. But now Einstein came along, and he's saying that the time interval between any two events could be different based on your frame of reference. This guy could measure less time it took for the light to travel than this guy. But they'll still all get the same speed, c. This is probably shaking your common sense notion of space and time. How could this be? But this is based on sound arguments. And in the next video, I'll explore more about time dilation and how to derive the time dilation formula. Stay tuned for the next one.